Welcome to Unacademy, the largest online e-learning platform, and welcome to Unacademy Semester Exams. We were discussing the network analysis and transmission lines crash course. In that, we were discussing the magnetic circuits, and today's topic is self and mutual inductance. Before that, let me tell you, I am sravan Kumar, having 7+ years of teaching experience and mentored more than 5K students for GATE and engineering services, and also cracked GATE. Let me also explain you about the Unacademy Learning App installation procedure. Welcome Srilata. Welcome Augustus. Welcome Soumya. Welcome to Network Analysis and Transmission Lines Crash Course. चलो अब देखते हैं Unacademy Learning App installation कैसे करना. So Unacademy Learning App, just type Unacademy Learning App in Google Play Store if you are an Android user and click on this install. If you are opting for GATE and engineering services, click on this and click on this plus and click get subscription. You'll have two types. One is plus and the iconic subscriptions. You'll get a dedicated mentor for your preparation. If you're opting for an iconic subscription, you can use my code as YSK10 to get the maximum discount of 10%, and you can click on this proceed to pay. If you click on proceed to pay, you have many options like debit card, credit cards, EMIs, UPI, wallets, and net banking. Using any of these platform, you can get subscription to the Unacademy. Let me tell you about this evolve for gate 2022. It's for the electrical batch A, English and Hindi. It starts on 21st of December. We have Ankit Goyal sir, Ajay Gupta sir, Hafiz sir, BB Reddy sir, as well as Suresh sir. You have top educators for these, and you can also get involved in this, and you can subscribe to this channel and get more information on this evolve for gate 2022. So let's see today's topic, and today's topic is self and mutual inductance. So before solving this self and mutual inductance, we'll just revise what we have done yesterday. In the previous session, we have seen what is a magnetic field, what are flux lines or field lines. I told you about magnetomotive force. Then we have discussed what was reluctance. Also, I told you about permeance, and also we have discussed what was magnetic flux density and magnetic field intensity. Then also we discussed what was permeability. Likewise, we have seen so many things. Let me tell you, the region around a magnet is the magnetic field, and the imaginary lines around the magnet or a current carrying conductor are the magnetic flux lines, and mmf is n into I. It is the force behind the production of the flux. Reluctance is S, which is mmf by flux, or you can also write it as Ni by phi. The flux lines you have here, and it is units are Webers, and the unit of magnetomotive force is ampere turn, and unit of this is ampere turn per Weber. Permeance is the reciprocal of reluctance, which is the ease with which the flux lines pass through, and it is given by phi by Ni, and the units would be Weber per ampere or ampere turn. Magnetic flux density is flux per unit area. It is Weber per meter square or Tesla. Magnetic field intensity is the strength or the weakness of the magnetic field at a given point. It is H is equal to Ni by L, and the units are ampere turn per meter. Permeability, it is denoted by mu, and mu is equal to mu naught into mu r, where mu naught is the absolute permeability and mu r is the relative permeability, and mu naught is equal to 4 pi into 10 power minus 7 Henry per meter, and also mu r is equal to 1 for free space, and it's a dimensionless quantity. So these are all the things that we have seen in the previous session. Let us solve some problems in this session on these basic questions. I'll just consider one question. So let's take one question and try to solve it. So the question is, a coil of 2000 turns, a coil of 2000 turns is wound uniformly over a non-magnetic ring, non-magnetic ring of mean circumference 80 centimeters, and cross sectional area of and the cross sectional area of 0.6 square centimeters. If the current through the coil is 2 amperes, if current through coil is 2 amperes, we are asked to calculate what is magnetizing force. Then we are asked to calculate reluctance. Then we are asked to calculate total flux, and then we are asked to find what is flux density. So first, whenever you are given a question like this, first you need to write what is given to you. What is the given data? N is equal to 200 turns, and mean circumference is length is 80 centimeters, and area A is equal to zero point 0.6 centimeter square, or A is equal to zero point 0.6 into 10 power minus 4 meter square. 80 centimeters, 80 into 10 power minus 2 meters. And also given current I is equal to 2 amperes. So these are some of the things, and let us consider mu r is equal to 1. So the first thing, what is that we need to find is magnetizing force. What is that we are asked to find? Magnetizing force, that is H is equal to N into I by L. What is N? 200. I is given as 2 and length is given as 80 into 10 power minus 2. So I want you guys to tell me it is 2 times, it is 4 times, 4, 5 times. So it is 5000 ampere turn per meter. You solve this, you'll get, so this is 2000, so number of turns is 2000, so it is 5000 ampere turns per meter. Now let us consider, so this is done. So the next one is reluctance. What is reluctance? Yes is equal to what? mmf by flux. What is mmf? Ni by flux. Is the flux given? No, flux is not given, so you need to find flux, or you can also use the other expression like S is equal to mu naught mu r into A. We have seen this expression yesterday. So L is already given as 80 into 10 power minus 2. Instead of using this, if you can use this, that would be get good. L by, so mu naught is 4 pi into 10 power minus 7, mu r 1, and area is given as 0.6 into 10 power minus 4. This will give you reluctance value of 1.06 into 10 power 10 ampere turn per Weber. Now let us see what is the third question given to us. Third question is total flux. What is the flux is equal to? Flux is equal to mmf by reluctance. mmf is n into I, so n is 2000 and I is 2, and reluctance we have found 1.06 into 10 power 10. So this will give you flux value of 0.377 micro Weber. And then we are asked to find flux density. So let us do this here only. Flux density B is equal to flux per area. What is the flux area? We have considered this. Flux is 0.33 into 10 power minus 6 micro, by area is 0.6 into 10 power minus 4. So this will give you B value of 6.2 into 10 power minus 3 Weber per meter square, or Tesla. So this is the question that is given to us. So once again, I'll just try to revise this. I'll just try to tell you. A coil of 200 turns is wound uniformly over a non-magnetic material of mean circumference 80 centimeters, and area of cross section is 0.6 centimeter square, and if the current is 2 amperes, We are asked to find what is the magnetizing force, reluctance, and total flux and flux density. So we have written all the things that are given to us. First, we have written what are given to us and converted the centimeters to meters in length and area. Then magnetizing force is H is equal to Ni by L. If you substitute, you'll get 5000 ampere turn per meter. And if you find reluctance, S is equal to, you can use mmf by flux, but you do not know flux. So you can use L by mu naught mu r into A expression, and by that you'll get 1.6 into 10 power 10 ampere turn per Weber. And you can use flux phi is equal to Ni by S. If you substitute N value, I value, and S value that we got here, you'll get 0.377 micro Weber. If you use flux is equal to flux density, you are asked to find flux density. Flux density is equal to flux by area. 0.33 into 10 power minus 6 is the micro Weber. 0.377. So this is 0.37 into 10 power minus 7 by zero point 0.6 into 10 power minus 4 will give you. Welcome Shivakumar, welcome Balraj and Manikanta. Welcome to Network Analysis and Transmission Lines. So with that you'll get 6.2 into 10 power minus 3 Weber per meter square or Tesla. So B is equal to 6.2 into 10 power minus 3 Tesla. So this is how you'll solve the problem. Let us take one more question and try to solve the problem. The question is, an iron ring has a cross section of 80 mm square, 80 square millimeter, and a mean length of 40 centimeters, and a mean length of 40 centimeters. It is wound with a coil of 500 turns. It is wound with a coil of 500 turns. Then for a current of 2 amperes through the coil, flux setup is 1.5. Flux setup is 1.5 milliweber. The question is 1.5 milliweber. Find the relative permeability of the iron. Question is, find relative permeability of iron. This is the question. So whenever you are given such a question, you need to write what is the iron has a cross section of 80. So area of cross section is 80 mm square. 80 mm square, and length is given as, what is the length given? Length is equal to 40 centimeters, and number of turns is also given as 500, and current as 2 amperes, and flux setup as 1.5 milliweber. Now you are asked to find permeability. We are relative permeability mu r is equal to how much? So from this you can write flux is equal to mmf by reluctance. What is mmf? Ni by S. Ni by S. We already know reluctance S is equal to L by mu naught mu r into A. Substitute S is equal to, you'll get 1 point, you need to flux, you need to substitute flux is equal to 1.5 into milliweber, 10 power minus 3 is equal to Ni 500 into 2 by S value. Substitute this S value in this. Flux is equal to Ni by S is equal to Ni by what is S? L by mu naught mu r into A. So if you substitute that, Ni by L 40 into 10 power minus 2 by mu naught 4 pi into 10 power minus 7 into mu r is what you need to find, and area is given as 80 millimeter square, so 80 into 10 power minus 6. From this you can find mu r is equal to 5968.31. It does not have any units, it is a dimensionless quantity. Thank you, Abhishek. Welcome to Network Analysis and Transmission Lines crash course. Thank you so much. So these are the two problems. Let me again tell you this. An iron ring has a cross section of 80 millimeters square and a mean length of 40 centimeters. It is wound with a coil of 500 turns for a current of 2 amperes. The flux setup is 1.5 milliweber. What is the relative permeability? So you can just write all the values that are given A, L, N, I, flux, and from this flux is equal to mmf by reluctance, that is Ni by S. You already know reluctance is equal to L by mu naught mu r into A. So you can just substitute in flux, and by substituting the values you'll get mu r is equal to 5968 5968.31. You'll get the value of relative permeability. Now let us look at something today that we are going to see is, first will I like to tell you what is electromagnetic induction. Electromagnetic induction. What is electromagnetic? First we'll see what is electromagnetic induction. The phenomena of cutting of flux by the conductor. The phenomenon of cutting of flux lines by the conductor to get the induced EMF in the conductor or coil is called electromagnetic induction. So what is electromagnetic induction? The phenomena of cutting of flux lines by the conductor. The phenomena of cutting of flux lines by the conductor to get the induced EMF in the conductor is called as the electromagnetic induction. That is simply you can say that the phenomena by which EMF is induced from flux is called as the electromagnetic induction, and there are from flux. Then we have what is called as Faraday's laws of electromagnetic induction. We have Faraday's laws of electromagnetic induction. What are Faraday's laws of electromagnetic induction? We have to see this. There are two laws. What is Faraday's laws of electromagnetic induction? Whenever the first law states that whenever the number of flux lines linking with a coil changes and EMF is induced in the coil. This is the first point. That means if you have number of flux lines which are linking with a conductor, let's call this is a conductor and these are the flux lines. The number of flux lines that are linking with the coil changes. If let's say this is rotating, so whenever it is placed in a magnetic field, you have a magnetic field and a conductor. Let's take some conductor that is placed as I have shown, and this is B, magnetic field, and this is the coil. Hi Raju, good evening. Whenever this flux linking with the coil changes, then an EMF is induced in this coil. That is the first Faraday's law. The second Faraday's law is the magnitude of EMF induced. The magnitude of EMF induced. The magnitude of EMF induced in the coil is directly proportional to the rate of change of flux. Let us say E is the EMF induced. It is directly proportional to the rate of change of flux. So here we'll introduce one term, that is flux linkage, generally denoted by lambda, which is flux linkage is equal to flux into number of turns of coil. Flux into number of turns of coil, that is lambda is equal to n into I. Flux, sorry, lambda is equal to n into phi. So this is the flux linkage. EMF is directly proportional to the rate of change of flux. Now if you look at this, as per the Lenz's law, there is a law called as Lenz's law or Lenz's law. It is simply the EMF, the induced EMF setup, that is an induced EMF sets up a current in such a direction so as to oppose the very cause producing it. So this is Lenz's law, that is E is proportional to d phi by dt, or E is equal to n d phi by dt. This was first and second law. Now what happens is this minus sign, this is opposes, this opposition, whatever is produced, it is in the opposite direction to the cause for it. So that is the reason this minus sign indicates is opposing, and it is given by Lenz's law. It is given by the Lenz's law. So EMF is gets induced in the conductor whenever there exists a change of flux. So depending on nature of methods, EMF induced can be classified as EMF induced is classified as the first one, based on the nature of methods, the EMF induced is classified as dynamically induced EMF and statically induced EMF. Dynamically induced EMF and statically induced EMF. So these are two types of EMFs that are induced. The first one is dynamically induced EMF. Dynamically induced EMF. In a dynamically induced EMF, the dynamic in the EMFs induced can be classified as dynamically induced EMF and statically induced EMF. In a dynamically induced EMF and in a statically induced EMF, in both the cases an EMF is induced in the conductor, and EMF is induced in both the statically and dynamically induced EMF, but the requirement in both the cases is rate of change of flux. The requirement in both the cases is rate of change of flux. There should always be a rate of change of flux. Rate of change of flux must exist. That means the flux that is being cut by the conductor, either you can keep the conductor stationary and flux is changing, or you can, in other words, you can say that the first case would be the flux is constant. The flux is constant and conductor is rotating. And in the second case, you can say the flux is changing and the conductor is stationary. So this is the difference between statically and dynamically induced EMF. In a dynamically induced EMF, the conductor or the coil is moving and flux is constant. Whereas in case of statically induced EMF, in case of a statically induced EMF, the flux is changing and the conductor is stationary. So these are the two different types of statically and dynamically induced EMF. And in statically induced EMF can further be classified as self-induced EMF and mutually induced EMF. So this is what we are learning: self and mutual inductance. Self and mutual inductance. Statically induced EMF and dynamically induced EMF. So statically and dynamically induced EMF. In statically induced EMF, the change in the flux lines with respect to the coil can be achieved without physically moving the coil. Such induced EMF in the coil, which is without the physical movement of the coil, is called as the statically induced EMF. So in this case, we have to see what is self-induced EMF and mutually induced EMF. Now this statically induced EMF is used in transformers and coupled circuits. So now let us see what is self-induced EMF and mutually induced EMF. Now let us see what is self-induced EMF and mutually induced EMF. Self-induced EMF Let us consider one coil. Let us consider a coil which is excited by some source, an AC source which is alternating in nature. Current is also alternating, and therefore the flux that is set up is also alternating in nature. And because of this current, there is a flux that is induced, there is a flux that is set up, and because of this flux there is an EMF induced in the coil. Because of this, there is an EMF that is induced in the coil, and this EMF is called as self-induced EMF. What is self-induced EMF? The EMF induced in the coil due to rate of change of flux in the same coil. The EMF induced in a coil due to rate of change of flux in the same coil. So what is self-induced EMF? EMF induced in a coil due to rate of change of flux in same coil is called as self-induced EMF. Now if you see what is mutually induced EMF or mutual inductance. Mutually induced EMF. Let us consider two circuits. There is one circuit, one coil which is placed adjacent to the other coil, and let there be some number of turns in both the coils which is excited by some AC source. Let the number of turns here be N1 and number of turns here be N2. Because of this supply, there is a current which is alternating in nature, and because of that, there is a flux that is induced in this. And because of this, two things will happen. One is EMF gets induced in same coil, that is self-induced EMF or self-inductance, or it is a property of the coil to oppose any change in current. Now, the other thing that will happen in this is, because you have an alternating voltage and there will be a current, because of that there will be a flux that is set up, and a part of this flux will also link this. A part of this flux, let us call this as coil 1 and let us call this as coil 2. Because of rate of change of flux and the flux that is in this coil, let us call that as phi 1, and because of that there is a flux that is set up in this coil that we'll call it as phi 2. So you have an induced EMF E1 here and induced EMF E2 here. So whenever you have rate of change of flux that is linking the second coil, that will link the second coil, there is an EMF that is induced in the second coil. So this process, EMF induced EMF induced in coil 2 due to rate of change of flux in first coil is called as mutual induction or mutually induced EMF or mutual inductance, mutually induced EMF. Now let us see about self-induced EMF. Karthik Jilla, good evening. Welcome to Network Analysis and Transmission Lines crash course. Now in a self-induced EMF, let us see you have sorry, you have a coil that is excited by some voltage source V, and let us say it has some n number of turns, and because of this voltage there is a current, and because of that current there is a flux that is set up, and this flux is directly proportional to the current. So this flux by current is a constant value. This flux by current is a constant value. Hence, the rate of change of flux is equal to K times the rate of change of current. So that is d phi by dt is equal to K into di by dt. And we know that according to Faraday's law, V is equal to minus N d phi by dt or minus N d phi by dt K into di by dt, or minus N, if you can substitute phi by I di by dt, and this is called as V is equal to minus L di by dt, where this V is equal to minus L di by dt, L is equal to N phi by I, which is called as self-inductance. This is called as self-inductance of the coil. This is called as the self-inductance of the coil, coefficient of self-inductance, and the property of the coil that opposes any change in the current flowing through it. So it is the property of coil, it is the property of the coil that opposes any change in current flowing is called self-inductance, and L is equal to N phi by I, and units are Henry. Vijay Dhawan, very good evening Vijay Dhawan. Because it is The induced EMF will oppose the cause for it. So that is the reason we have taken minus. We have taken minus. Just look back here. I have told you about this minus here and Lenz's law. The induced EMF sets up a current in the such a direction that so as to oppose the very cause for it, cause producing it. So this is the reason why we are taking a negative sign here. According to Lenz's law. According to Lenz's law, we are taking a negative sign. Now let's look at mutual induc mutual inductance. As I told you, we have two coils, the first coil and a second coil. यहाँ पे दो coil है यहाँ पे. So ये हुआ coil 1 और ये हुआ coil 2 और इन दोनों में एक common flux flow होगी. इसको मैं supply दे रहा हूँ यहाँ पे B and there is a current here. Because of that there is a flux that is set up. We'll call the flux that is being linking with the first coil as phi 1 and the flux that is linking with the coil 2 as flux phi 2. Let us say we have n1 number of turns in first coil and let us say we have n2 number of turns in the second coil. Hope Vijay Dhawan your doubt is clear. Why we have taken that negative sign? It is because of the Lenz's law that we have taken the negative sign. So you can say mutual inductance. Now we'll try to do this. The flux in the second coil is due to the current in the first coil. So can we write F2 by I1 is a constant value, or sorry, phi 2 by I1 is equal to K into I1. And as we know that rate of change of flux is equal to K times rate of change of current. That is, what is rate of change of flux? D phi by dt. That is d phi 2 by dt is equal to K into what is rate of change of current? Because the current is in the first coil, we have taken K into di by dt. So d phi 2 by dt is equal to K into di1 by dt. Phi 2 we are getting flux in the second coil because of the current in the first coil. But we already know what is K is equal to. K is equal to, just now we have seen what is K is equal to phi 2 by I1. Phi 2 by I1. So you can write d phi 2 by dt is equal to K phi 2 by I1 into di by dt. Phi 2 by I1 into di by dt. So voltage V2 is equal to, that is we have the first coil and we have the second coil and there is a voltage V2 that is set up, and V2 is equal to minus N2 d phi 2 by dt minus N2. What is d phi 2 by dt? You can substitute this d phi 2 by dt here. That is phi 2 by I1 into di by dt. So we can write V2 is equal to minus m di by dt. This is di1, so you'll have a di1. This is also di1, where m is equal to n2 phi 2 by I1. What is m is equal to? N2 phi 2 by I1, which is the coefficient of mutual inductance, where m is equal to n2 phi 2 by I1. So we have done. What is L is equal to n phi by I. This is n1 phi 1 by I1. That is nothing but, because we are having the flux and current in the same coil, and even the number of turns, if you see this number of turns, flux and current, everything is in the same coil. And if you take this, you have two coils n1 and n2. Flux in the second coil is because of the current in the first coil, so you can write it as a constant, and the rate of change of flux is equal to K into rate of change of current. And what is phi 2 by d phi 2 by dt is equal to K into di1 by dt. From this you can write K is equal to phi 2 by I here, that is di1 by dt. And if you take the, according to Faraday's laws of electromagnetic induction. Induced EMF can be written as V2 is equal to minus N2 d phi 2 by dt, and N2 d phi 2 by dt is here. It is phi 2 by I1 into di1 by dt. So you'll get V2 is equal to, we are calling this as a constant M. So M is equal to N2 phi 2 by I1. Hope this point is clear. Now let us look at inductance in series and inductance in parallel, considering the mutual inductance. Now let us say there are 2 points here. One is aiding and the other one is opposing. Let us say you have two coils that are connected in this way. In this, if the current is passing through this, and if the flux in the first coil aids flux in the second coil, the resultant flux is the sum of the two fluxes, then it is an aiding. If you have the resultant flux is the difference of the two, then it is opposing. So based on this, you have four combinations. One is series aiding, second series opposing, third parallel aiding, and parallel opposing. Because this is a crash course, we cannot derive all these. I'll give you the expressions for all these and also tell you. So let us say you have two coils with inductances L1 and L2, and let us assume that they are in series aiding. You'll understand about this series aiding and opposing. So the L equivalent can be written as L1 plus L2 plus 2M. We have two mutual inductance. The mutual inductance between them is M. This is the first case. Now coming to the second case, if we have two coils whose fluxes are opposing, we call it as series opposing, and L equivalent is L1 plus L2 minus 2M. Let us consider you have two, you can even draw this something like this. We have two coils in this way. This is L1 and this is L2. And if you have two coils which are connected in parallel, let us say this is L1 and this is L2, and let us assume that this is parallel aiding, that is the two fluxes in the coils are aiding. So L1 L2 minus M by L1 plus L2 minus 2M. This is the expression for parallel aiding. And let us say if you have two coils, let's say they are something connected like this, and you'll understand this concept when you learn dot convention. And let us assume that this inductance is L1 and this inductance is L2, and let us say they are parallel opposing. We'll also look at this, and L equivalent, can say L equivalent or you can say just L is equal to L1 L2 minus M square by L1 plus L2 plus 2M. So once again, there are two types. One is aiding and the other one is opposing, and it is based on the type of the connection, whether the flux in both the coils is aiding or flux in both the coils is opposing. We have four types. One is series aiding, series opposing, parallel aiding, and parallel opposing. So based on this concept, you can see the equivalent inductance, including the mutual inductance. So you have L1 L2 in series, whose flux is the resultant phi 1 plus phi 2. Phi 1 is the flux in the first coil and phi 2 is the flux in the second coil. If you say this is phi 1 and this is phi 2 flux, the resultant flux is the difference of the two fluxes. So it is called as series opposing, and this is the expression for that. Equivalent inductance will be L1 plus L2 minus 2M. And if you have two inductors which are connected in parallel and their fluxes are aiding, then you have L is equal to L1 L2 minus M square by L1 plus L2 minus 2M. And if you have two inductors that are connected in parallel and whose fluxes are opposing, that is a parallel opposition, it is L is equal to L1 L2 minus M square by L1 plus L2 plus 2M. So based on this, let us solve one question based on this concept of series aiding, series opposing, parallel aiding and parallel opposing. There is a question that is given something like this. The question is, the combined inductance of two coils connected in the combined inductance of two coils connected in series is 0.6 Henry or 0.1 Henry, depending on the relative direction of the currents. Depending on relative depending on the relative direction of currents. If one of the coil has self-inductance of if one of the coil has self-inductance of 0.2 Henry, find the mutual inductance. Question is, find mutual inductance. This is the question. So let us read the question once again. It is given that the combined inductance is 0.6, two coils connected in series. That means there are two coils that are connected in series. They are connected once like this, and let's say they are also connected. This is also a series combination like this. And he gave us that the resultant L here is, that is L1 plus L2 plus 2M is equal to, because 0.6 is higher and it is 0.6 Henry, and L is equal to L1 plus L2 plus minus 2M gave us 0.1 Henry. This is the question. This is L1, this is L2 and the mutual inductance M. L1, L2 and the mutual inductance is M. So what does this is what? This is series aiding. And what is this? Series opposing. If you try to calculate this, see, that is L1 plus L2 plus L2 plus 2M is equal to 0.6 Henry, and L1, let's write this, L1 plus L2 minus 2M is equal to 0.1 Henry. Also he gave us one more thing, the self inductance of the one of the coil is 0.2 Henry. So L1 L2 both are same. Let us take L1 is equal to 0.2 Henry and let's substitute it here. Therefore 0.2 plus L2 plus 2M is equal to 0.6, and let's also write the other equation, 0.2 plus L2 minus 2M is equal to 0.1 Henry. Now let's simplify this. L2 plus 2M is equal to 0.4, L2 minus 2M is equal to minus 0.1, because if this point is 0.2 comes to the right side, it is minus 0.2. So 0.1 minus 0.2 is minus 0.1. So let's simplify this. This is L2 minus 2M is equal to minus 0.1. If we cancel this, 2L2 is equal to 0.3. So L2 is equal to 0.15 Henry. L2 is equal to 0.15 Henry. This is what we got it. So what is the value of this mutual inductance that is asked? It is M is equal to, Find the mutual inductance. So we have found self-inductance L. So we have got self-inductance L2 first. What is the value of L2 that we got? 0.15 Henry. So from this, you already know these two equations. This is one equation. Substitute L2 value to find M value. So let's take L2 plus 2M is equal to 0.4. L2 plus 2M is equal to 0.4. We are asked to find M value. So 2M is equal to 0.4 minus L2. If you go back, L2 is 0.15. So 2M is equal to 0.4 minus 0.15. So it is 0.25 by 2. So M is equal to 0.125 Henry. So the answer is 0.125 Henry. So this is M is equal to 0.125 Henry. So let us see once again what is given to us. It is the combined inductance of the two coils connected in series is given as 0.6 and 0.1. You can understand this is series aiding and this is series opposing depending on the relative direction of the currents. If one of the coils has the self inductance as 0.2, so one coil already has given, that is L1 or L2 can be taken as 0.2 Henry. So when they are in series aiding, it is because they are connected in series. When they are series aiding, it is 0.6, and when they are series opposing, it is 0.1. Now when you just try to simplify these two by substituting either L1 or L2 is equal to 0.1, you'll get L2 is equal to 0.15 Henry. And if you substitute the same L2 value in this expression, you substitute this L2 value in this expression as what is the value of L2? L2 is equal to 0.15 Henry. If you substitute this in this, you'll get M value as 0.125 Henry. 0.125 Henry. So this is one question that is based on the given data. And let's also take one more question. Two coils of inductances. Two coils of inductance 0.1 Henry and 0.2 Henry are connected in four different ways as follows. That is series aiding. One is series aiding. Second, series opposing. Third, parallel aiding. Fourth, parallel opposition. Now if the mutual inductance between them is 0.05 Henry, find the equivalent inductance. Find the equivalent inductance. So in the first case, we already know when we have series aiding, it is L is equal to L1 plus L2 plus 2M. Just substitute the values 0.1 plus 0.2 plus 2 into 0.05. You'll get this value. When you have series opposition, L is equal to L1 plus L2 minus 2M. So 0.1 plus 0.2 minus 2 into 0.05. You'll get this as Henry's. I want you to solve this. And when you have parallel aiding, it is equivalent is equal to L1 L2 minus M square by L1 plus L2 minus 2M. Substitute this value of L1 as 0.1, L2 as 0.2 minus m square 0.05 square by L1 zero point 0.1 plus L2 zero point 0.2 minus 2 into m. You can substitute this series opposition value also. 0.05 will give you this Henry's. So I just want you to solve this, and when you have the fourth combination as parallel opposition, I want you to tell me what is the expression for that parallel combination. Good evening SVS online education. When you have parallel opposition, L is equal to L1 L2 minus m square by L1 plus L2 L1 plus L2 plus 2m. Just substitute the value of L1 0.1 into 0.2 L2, and this is 0.05 square by, probably I have taken some random values. If you get just negative values, ignore them. L1 is 0.1 plus L2 is 0.2 plus 2 into 0.05. We'll get this Henry's. This is how, this is a method to solve the given problem. This is one of the important questions that is generally asked with some perfect values that will be given in your examinations. Also, this is also one of the important questions that is frequently asked in your semester exams. So these two are very important, and let's see what we have seen today. One is we have solved problem on S is equal to L by mu naught mu r into A, or we also know S is equal to Ni by flux. In the second, also we used flux and flux density relationship to find the flux, and I told you about electromagnetic induction. I discussed about electromagnetic induction, and we also seen what is static and dynamically induced EMF, statically and dynamically induced EMF. And we have seen in statically induced EMF we have self-induced EMF and mutually induced EMF, and we have seen what is self-inductance and mutual inductance. This is N phi by I, and this is N2 phi 2 by I1, both having the units of Henrys. Then we have taken a combination of inductance connected in inductors connected in series aiding, series opposition, parallel aiding, parallel opposition, and their expressions, and try to solve two problems on this concept. So these are some of the things that we have learned today on self and mutual inductance. So as I always tell you, we have India's #1 study channels in Creatrix GATE EEE ECE and Instrumentation, Unacademy GATE ME PIXE, Unacademy GATE CE, Unacademy GATE Telugu, Unacademy SSC JE, Unacademy Computer Science, Unacademy GATE Questions, Electrical Junction, Unacademy Engineering Foundation, Unacademy Engineering Pathshala, and Unacademy Semester Exams. So I would like to request you to like the video, share the video, and use my code YSK10 to get the maximum discount of 10% on Unacademy subscription. And also request you to please subscribe to our channel and click on this bell icon to get notification of my classes. Once again, thank you all. Thank you for joining me this session on self and mutual inductance. Also, once again, I'll remind you of the Evolve for GATE 2022 for Electrical Batch A, which will be held both in English and Hindi, and it starts from the 21st December by our top educators like Ankit Goyal sir, Ajay Gupta sir, Hafiz sir, and BV Reddy sir and Suresh sir. Will have this is an excellent opportunity for all of you to get subscribed to Unacademy and get to know about this Evolve batch. And there is also basic foundation course that is being started. So please do use this opportunity and Get subscribed to an academy. And once again, thank you all. Thank you for joining me today on this session of network analysis and transmission lines magnetic circuits topic. We have discussed self and mutual inductance and problems based on them. Thank you so much.